This video will tell you about how to detect lines in your images. So let's say you've got images like this. You've done your edge detection, you've run Canny like from the previous video, and you've found a bunch of edges in your image. And you want to use these edges to be able to figure out, are you pointing straight down this lane or not? How far are you from the sides of the lane? It's difficult to say from just this image. What we need to do is figure out the equation of each of these lines so that we know where we are in relation to the lines in the image, so we can start to plot things actually in the image. And that's actually relatively straightforward to do. So first off, let's think about what is a line. Well, of course, a line is y equals mx plus b, and if I give you y equals mx plus b in a point, you can tell me if that point is on the line by using that equation. So this is great if you happen to have the line already, but what do we do if we have just a bunch of points? And we have a couple of options here. One is that we can do linear regression or something like that, line of best fit. We can figure out what line best fits these points. We can also propose a bunch of prototype lines and try to figure out, based on these prototype lines, which of them fits the best, and then maybe do some refining steps. And if there's many different lines in your image, so you have a whole bunch of points that could potentially become many different lines, it turns out it's generally best to propose a couple of prototype lines or cast out all the possible lines and see which fits better. So let's play with that in this little example here. So we draw a line at random across the image. It doesn't cross any of the points, clearly a bad fit. Maybe we choose to shift it a little bit over, still not there, but then we eventually hit a spot where we've got some points and play with some rotations, and eventually we get a pretty good fit. We're under 5 or 6 points here, good enough. We want to see, how about that cross piece there? We certainly haven't accounted for every point in this way. So let's play with a couple of lines going the other direction. Not a great fit, only a couple of points. Move it a little bit more, move it a little bit more, and then we eventually end up with a good fit and 2 good lines using this method. So this is in essence what the Hopf transform does. With the Hopf transform, you're given a discrete space like an image, so you have a finite set of lines, and you enumerate all of those possible lines in that image. Then you create a matrix with these lines, and you add a column to the matrix to enumerate how many points are underneath these lines. So you initialize that to 0. So you create this list of all possible lines and then a column next to them so that you can enumerate how many points can possibly be under it. Then you cast these lines across your image, and you count up, as you're tracking the line across the image, how many of the pixels underneath it are on. So note that we're saying on here. This implies a binary image. So it's either on or off. It's either white, which is on, or black, which is off. And by counting these up, you can see if a line exists in this image or not. So if you cast a line across the image and you see that most of the points on the line are on, then it's probably an actual line in the image. If most of the points are off, then it's probably not. Ultimately, you set a threshold so that you can get as many possible lines without taking on the unlikely lines in your image. You may still get some spurious ones, but in general, you want to set a threshold smartly so you can avoid that. Let's play with this a little bit. So let's say we have a 4x4 image here. First thing we'd want to do is just look at it and enumerate all the possible lines. So there's 7 lines from here, going from the start point in the bottom left to all possible endpoints in the image. 9 lines from the next pixel over, and so on and so on. We're not going to draw all of them in this particular video because that would take a long time. So what if we color in some of this image? So we have a bunch of off pixels here, the black pixels, and 3 on pixels. And as a human, you can pretty clearly see where the line is in this image, but how does the computer figure this out? Well, we're going to cast a set of lines across it. We're not going to look at all the possible lines in this so that we can save a little bit of time, but we're going to cast a couple lines across it. And we look at this one here. We throw a diagonal line from the bottom left to the top right. How many pixels is under that? Just 1. So this probably isn't a line, right? You'd probably want your threshold here to be maybe 2, maybe 3, depending on how big of a line you want, but 1 pixel certainly doesn't make an actual line. Cast another line, still 1, still probably not an actual line, so we can disregard this. Another line, this one gets 0, no pixels on underneath it, all black pixels, so definitely not a line. Play around, do the opposite diagonal, and note that these lines actually have 0 width, so they don't intersect with the white pixels at all here, so this is still 0. Cast a little bit of a steeper slope here, and this particular line has 2 pixels underneath it, so could be a line. But if we play around with it a little bit more, then we'll get to the 3 pixels here, and we can call this a success. We do see that there are 3 on pixels underneath this line, so it's probably an actual line. So we need a binary image for this, which means we need to do some preparation for the Hoff transform. And in past videos we talked about how to filter an image and how to do edge detection, so let's see how we can combine these things in a logical way so we can get a nice binary image that just shows possible things that could be lines that we want to look at. So in case of our lane detector that we're developing, we first want to filter the image for white or yellow in this case to find the white lines, the yellow lines. Obviously if you're looking for different colors you'd want to look for different things to filter here, but that's what we start with here. So we come up with this nice filtered image on the left here. Now what would happen if we ran a Hoff transform across this right now? Well, because the white part is so thick, it would find all of the lines hidden within this. So yes, there would be a nice one on the boundary here, which is what we're looking for, but there'd also be a handful of lines going diagonally across it and every which way, all the way across this spot here, and we wouldn't really be able to tell which of those is the real line that we're looking for. Which one marks the edge of the lane. So fortunately, we know how to do edge detection, and that gives us all the possible edges in the image. So this gives us a really strong edge right here that we can use, and also the yellow lane marker edges and the edges around the duckies and all these other things in the image here. So let's put these two together. If we use a bitwise AND on these two images, then we can combine them and come up with an image that is just the edges corresponding to the white lane markers. Now note that you may have to go back, revisit your filtering step a little bit, because if your filtering on the white step here doesn't completely overlap the line, then you're not going to end up with anything on this final image here. So you may want to go back and dilate your images just a little bit more, or run a Gaussian filter on them or something like that to get a better filter here that is a little bit bigger than it should be so that it does definitely overlap with these edges. And after we do this, we can run the Hoff transform and get some lines out of this. So let's talk about how to do this in OpenCV, because that's what you're probably going to be using for these assignments. OpenCV has two different functions we can use for Hoff lines to find Hoff transforms. One of them is this CV2 Hoff lines, and you take in the image, of course, and the image should be 8-bit and it should be single channel binary. So on or off, 0 or 255, that's it. It returns a vector of lines, so in Python that would be a list of lines. And each line has two different elements inside of it, rho and theta. So this means that you get back the answer in polar coordinates. So the distance it is from the coordinates origin and the angle of the line in your image. If you think about how Hoff transforms create lines and put them across it, this makes a lot of sense for why they would give it to you that way. We're going to talk about another method in just a minute that doesn't have this problem, but if you do end up using the CV2 Hoff lines, then it's going to give you everything back in polar coordinates. You also can give it a rho, which is the resolution you want for the distance. People usually use about 1 for this, 1 pixel, so we look at all possible lines in the image. And then a theta, which is the angular resolution, and people usually use about 1 degree. This is in radians, so that would be pi over 180, but about 1 degree is pretty good in general. Your big knob to tune here, though, is the threshold. So this is how many pixels have to be on to count this as a line. So how many pixels vote towards this line? If it's below that, it doesn't return this in lines. If it's above that, it returns it in lines. So this is the big thing you want to play with to get a good answer from Hoff lines. And of course, you can look at the documentation on the OpenCV website to learn more about this. Alright, so we talked about the Hoff transform, but if you're thinking about this, if you're looking at what we're actually doing in this, it seems like it's going to take a lot of processing power. We have a lot of searching to do. We enumerate all possible lines in an image. We have to then treat all possible lines equally, go through each one of them, go through the entire image with each one of them. It takes a lot of time. Fortunately, other people have come up with a probabilistic way of doing this. So instead of searching for every possible line, we can randomly sample over the space and then figure out, based on the results from one line, should we keep looking in that region or not. So if you cast a line across an image and no pixels are on underneath it, you probably don't need to look at the next couple of rhos and thetas to figure out if there's anything in the nearby neighborhood. You can probably skip a few and move on. So by sampling over the image and then using that to feed our next sample, we can figure out which lines are actually in the image without having to look at absolutely everything. And of course, this saves valuable computational resources, especially on embedded systems like the Raspberry Pi and your DuckyBot. So the probabilistic Hoff transform in OpenCV is a very similar function signature with a few extra knobs we can turn. So this one's called Hofflines P, and it still takes in the image, same thing, 8-bit, single channel, binary, just wants 0 and 255. It still gives you lines as an output list, but in this case, each line has a 4-element vector that's in Cartesian format, so a little bit easier for you to process probably and draw in the image. So this will give you the actual pixel coordinates for the start and end point of each line it finds. So x1, y1 is the start coordinate, x2, y2 is the end coordinate for every line segment that it finds in the image. And note that this is looking for line segments now, not actual infinitely long lines across your image too. You can still tune rho if you want. As noted here, usually rho is about 1, and you can still tune theta if you want. Usually people use about 1 degree here as your theta resolution. You still have a threshold that you can use in the exact same way. So the algorithm still works in the same way, where the pixels vote on how many of them are underneath the line, and then you use that to figure out whether this is a line or not. But you have two other knobs we can tune as well as this, one of them which is min line length. So minimum line length is the minimum length of that line segment to count as a line. Now you might ask, what's the difference between that and the threshold? Well, with the probabilistic Hopf transform, we also have the concept of skipping a few pixels in between. So you might have gaps between pixels because image processing algorithms aren't perfect and may not register every single edge in the image. If you go back to some of our prior images in this lecture, you can see that some of them have some gaps in them. We still want to be able to account for that. So you can increase maximum line gap in order to account for some of these lines that might have some small holes in them. And by tuning these three parameters, you should be able to get a pretty good answer for where the lines are in your image and find the lanes in the images given. And of course, you can look at the documentation on the OpenCV website here as well. So what does this look like when we're done? Well, on the left-hand side, you can see the white lines in the image. This is from the images taken earlier in this lecture. And you can see blue where the lines are, green where the lines start, and red where the lines end. A lot of them overlap, and that's to be expected. But these are still valuable for you to use so that you can find the actual equations of the lines here. Same on the yellow ones. Note that on the yellow lines, it'll also find the horizontal lines, so that if you're building your own lane filter, like in Duckytown, then you'd want to eliminate some of those using a method of your choice. So let's review. Hopf transforms will cast all possible lines across an image or probabilistically cast them across an image to try to find all the actual lines in your image. So it casts a bunch of prototype lines, counts the number of on pixels underneath to figure out which ones are actually lines or not. To prepare an image for the Hopf transform, you want to ensure that it only consists of the edges you want to consider. So if you're looking for all the white lane markers, you want to make sure it only has white edges in it. If you're looking for the yellow lane markers, yellow edges, and so on. And then the probabilistic Hopf transform is faster than the traditional method and recommended for this class. And this should give you enough to be able to develop your own line detector to figure out where the lanes are in the images given to you for your homeworks and projects.